Oh, good afternoon, Internet. Welcome, welcome to NL Mathman's Math Help Stream. Um, yes, here behind me today, like I was saying, I've got a very nice picture of Flurry and Smokey out. They were out swimming. I can't recall where this one was taken. This is not at the cabin because we don't have like a dock or anything like that at the cabin. You'll see that I have moved. Like I said, I moved my stream start soon bit down. Right? I couldn't put it over Smokey's face. It'd be very rude over little guy, right? But when Flurry goes out for a swim, you can see her behind me. She goes on out the pond, but she gets really wet because she goes right out in the center and just paddles around, proper dog paddle like you would see. Whereas Smokey, he doesn't tend to go out very far. He just sort of treads water a little bit, sort of walks out and then stops, right? I guess it's because of the difference in his fur, right? Because Flurry here is being a lab husky, right? The water just sort of sheds off her afterwards. Whereas for Smokey, it really sticks to him, right? He stays he ends up staying wet for a long time after he's out in the pond. So you know maybe that's why. Maybe that's why he has a bit of an aversion to water. Whereas Flurry loves it. Anyway, today, like it says over here on the side, I'm not gonna take a whole lot of time just rambling on about stuff before I get started here today. I'm gonna get into talking about normal distribution and z-scores. We're going to do a bit more recap on counting problems. That'll be factorials, but I'm mostly going to be focusing on the algebra behind them today. So a few brief ones on that. And then if we've got time, which we probably will today, I will get on and do a bit on the volume of regular shapes. That one just needs to be done, I guess, in the next little while so I can send out the video, but the student is not quite on to those ones yet. Right? So, like I said, for today then, I will start off with the normal distribution and the z-scores. So the normal distribution, like we were talking about previously, is, oh, let me get my camera there, zoomed on in, twisted to the side. All right, there we go. So the normal distribution, and this is on Betty Ann. Let's see, this is page 278 in your textbook, so this is a good one to take a look at. This really summarizes what we're dealing with when we're talking about the normal distribution, right? So it's a bell curve, which it is sometimes called instead of a normal distribution, and it roughly has 34, 14, and 2% of the data in these areas here. Now, your book is a bit more accurate about it, right? Your book doesn't do the 34, 14, and 2, which is sort of the rule of thumb that we tell students to remember. The book goes into a bit more detail and does, as you see here, 68, 95, and 99.7. What this is telling us is the amount of the data that is between how many standard deviations away from the mean, right? We see these symbols down here. This is, of course, mu meaning the mean, right? I know it's a bit annoying. Sometimes they use mu, sometimes they use x bar. They mean the same thing. They mean mean, right? And we see here, this is the difference of one standard deviation below, because that's what this symbol means. That's one standard deviation right there. And this is one standard deviation above. And we notice over here, right, within one standard deviation of the mean, if a group of data is normally distributed, there's going to be 68% of the data is going to be between one standard deviation below and one standard deviation above, right? The reason it's 34 is, of course, 34 is half of 68, right? So from the standard deviation, or sorry, from the median, Jesus, from the mean, from the mean, one standard deviation down, it's 34% of the data. From the mean one up is 34, right? And if we go beyond that, right, so the next standard deviation up, as we see here, is about 13.5%, right? So that's between one standard deviation up and two standard deviations up. There's 13.5, right? And we can use this graph and this rule of thumb, which it's not really a rule of thumb per se, because this is exactly accurate to if the data is actually normally distributed, right? Not all data, not even all large groups of data are going to be normally distributed. And even those that are, the normal distribution itself tends to be a bit of an approximation, but it's close enough to be correct a lot of the time, especially as groups of data get really big, right? And as you see here, we've got 68, 95, and 99.7. So within three standard deviations of the mean, you have 99.7% of your data. So only 0.3% is greater than 3 away from the mean, right? Like it says here, generally measurements of living things such as mass, height, and length have a normal distribution. That's true, yes, because in large populations, generally whatever the median is or the mean, right? The numbers clump around it in the same way that the normal distribution clumps, sort of in the center like that, right? So based on this just rule about the normal distribution, we can go ahead and we can answer several questions like the ones that they ask in your book. Now, I do want to talk about this a little bit, like I said, before I get on to talking about Z-scores, because Z-scores are just a more thorough way of interpreting the normal distribution, right? But then let's do a question on here from the textbook. This is one of the ones that you were told to do in your notes. So I'm going to do question 1 over here. The ages of members of a seniors curling club are normally distributed with a mean of 63 years and a standard deviation of 4 years. Okay? So this is Math 2101B Unit 2, like so. And this is going to be page, what did I say? This was 2. It doesn't say over on the side, it just says page 10 because of the way these PDFs work. Page 279. 279. This is going to be question 1. Well, whenever we're approached with a question like this, like I say for a lot of things, when in doubt, draw it out, right? It always helps to draw out a diagram for a situation like this. So let's go ahead and do out a rough normal distribution over here. Really rough. It doesn't matter. It doesn't matter how rough it is, right? We'll just kind of do out a bell curve. And then let's go through and let's label the diagram, because that's the point of doing out the curve like this, is to label it. Right, so this is going to be my mean here. So this is going to be x bar. This is going to be 1 standard deviation away, 2 standard deviations away, 3 standard deviations away. Now I know that the dotted lines I'm drawing don't quite line up with each other or with what the the actual way that the normal distribution will be laid out. But like I said, it's just an approximation to give us a visual that we can look off of to understand what's going on here, right? So the ages of members of a seniors curling club normally distributed. The mean is 63. Okay, so we can put 63 here for the middle one, and a standard deviation of 4. Okay, so now once we have this standard deviation, we can go and we can start labeling the rest of these, right? So we know that it's going to be 4 difference for each of these, 4 up, and it's going to be 4 down for each of those, right? So this is going to be 67, this is going to be 71, this is going to be 75. Then going down, we're going to have 59, 55, and 51. Okay? So this is the sort of a more full representation of the situation. And with this now, we can more easily answer questions A, B, and C. Because between 55 and 63 years old, well, 55 is here, which is 2 standard deviations down. 63 is the mean itself, right? So if we look back over at our, hold on. I'm going to write that down so we have that to refer to. If we scroll back up, which is just on the previous page of the book, and look at our diagram again, we know that, well, this section here, right? Let me label this in, let me label it in a different color. This is going to be 34% roughly, and this one's going to be 34%, right? We know this is going to be roughly 13.5% there, and another 13.5% here. And we know that these last ones here are roughly, they put down 2.35. Okay, I'll go with that. I like the more accurate representations. So 2.35% for both those. There we go. So now we're looking from 55 to 63. Well, that's going to be this section here from 55 to 59 plus this section here, 59 to 63. So it's going to be these two numbers added together, right? So it's going to be 13.5% plus 34%. It's going to equal 47.5%. There we go. Right? So for question 1A then, what percent of the curlers is between 55 and 63? Well, 47.5%. right? So part B then, 67 to 75. Well, that's going to be these two sections over here, right? We've got our 67 here, we've got our 75 here. You might be seeing now how drawing out the diagram makes these questions pretty easy, because now we've just got to add these two numbers together. That's going to be 13.5% plus 2.35%. It's going to be 15.85%. And don't worry about significant figures or anything like that. In these situations, we don't need to round this one to 15.9, just like we didn't round this one to. This one would actually round to 47, as you'll see later on, Troy, if you're still watching. But in physics, when something is exactly 0.5, we actually round that one down. When it's anything marginally above 0.5, we round that up. And that's just a rule of thumb, of course. Different industries will have different rules for rounding. See, like I mentioned before, aircraft, like refueling, always rounds down because it's totally fine to tell the pilot that he's got a little bit, tell him he's got less fuel than he actually does. But if you tell him he's got more fuel than he does, and you do that a bunch of times over and over again, eventually it's going to add up and it's going to cause a real problem. Anyway, rounding is weird, is my point. But here we're not gonna bother with the rounding because as far as we're concerned, these values from the normal distribution are exact, right? So they don't need to be rounded because they don't have any significant figures. Then older than 75, well, that's going to be here 75 plus. It's going to be out here, so that's going to be about 0.15%, right? And I didn't fill those in, but let's go ahead and fill those ones in over here. This is 0.15%. And this is 0.15%. I know it doesn't list that one above, sort of. It sort of doesn't list it, but it kind of does, right? Because if you look over here, there's 99.7% taken care of in all this section. So it means the remaining 0.3% has got to be split between here and here, and it's split equally because it's the normal distribution. It's always split equally. So it's going to be 0.3 divided by 2, or 0.15 here and 0.15 here. Right? Like I said, stop me at any point if you want me to talk about, say, a different question here. Now, your book doesn't ask you to do a ton of these questions in this section. Your guide actually quickly, after we get through this part, goes on and starts talking about z-scores. So that is what I'm going to focus on today for this section. Let me scroll on down there now. I'm just going to have to just bear with me. I could mute the mic, but you know what? I'll treat you to the lovely scrolling sounds of my wonderful mouse. Oh, right, it's not even in that file. Oh, there was another one that I meant to open. Oh, well, hold on, Twitch chat. Hold on. Hold on real quick there. I thought for sure I had all the ones open that I needed, but, you know, we all make mistakes, especially me. There we go, z-scores. See? That's the one I wanted. Hear the wonderful, wonderful scrolling sounds? Listen to that. Isn't that great? I think I've showed you my mouse before, right? Look at that. See, it's a vertical mouse. So you hold it like this, right? It's great. It does wonders. It does wonders for carpal tunnel. Let me tell you, for repetitive strain injury and stuff like that. This is a lot. This is a Logitech one that I got, but it's the MX Vertical. But just vertical mice in general, there's lots of different varieties, and you can get them on Amazon or whatever. And because you hold your hand like this, like a hand, instead of having your wrist turned like this, because right, see the difference in the elbow, right? Like I've got it like this, so my elbow is nice and straight. But if I turn it, then I'm twisting right here, and it puts a lot of strain on that tendon over here to have your arm turned like this constantly, right? But if you do it like this, MX Ergo trackball, oh yeah, those are nice too, absolutely. Da, 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 da. Okay, yeah, Ergo trackball, yeah, those are really nice. Yeah, one of my good friends uses a trackball a lot. I could never really get used to it, but I can see how that can be, you know, um, that can be a really good thing for ergonomics as well, for sure. Anyway, so Z scores, right? I should actually. This is the page that I wanted. I got a little touch distracted there. But so a Z score really is just the same as those questions we were just doing here. You know how we did -1 standard deviation down, 2 standard deviations down, 3 down? Well, how about they did 1.5, right? Or how about it did 2.37 standard deviations up, right? Is it always going to be whole numbers, like one standard deviation up, two up? No, it's not. It's not always going to be. And because of that, we use z-scores. Now, because this is stats and statisticians don't like doing math actually, we don't actually need to go and use like an integral or anything like that and calculate the area under the curve and then find a certain percentage of it or any such stuff like that. We don't have to do any of that. All we got to do is look up the z-scores in a table, right? Because we're doing stats now. So we don't actually have to do a whole lot of like mathy math. We just look things up in a chart. It's great. So what we've got to do, all a z-score is it basically allows us to pick any amount of standard deviations away from the mean and not just whole numbers, right? So a z-score indicates the number of standard deviations that a data value lies from the mean, calculated using this formula. So the z-score is equal to, right, so let me just write this down. I'll use a different color here. So the z-score is going to be equal to your value, subtract your mean, divided by your standard deviation. Now I know that looks way more complicated than it is because it's a whole bunch of different symbols there. But all it means is we just take whatever value we've got, we find out how far it is away from the mean, and then we divide it by the standard deviation just to find out how many standard deviations away from the mean it is. That's all we got to do there, right? It's really not a big deal. And then once we do that, we take that value and look it up in a table, and then that table tells us what percent of the normal distribution lies to the left. And that's the tricky bit. That's the bit that trips people up a lot. Is you got to remember that the z-score only. Oh, my pen's invisible again! Hooray! Look at that. Oh, now I'm holding nothing. Now there's a hole in my head. Look at that. Literally and metaphorically. I mean, I guess everybody's got several holes in their head, right? Like, I mean, two nostrils, a mouth, two ears, and it's arguably the eyes, right? That's 5 to 7, depending on how you define them. Anyway, I got extra ones though. Loads of extra holes in my head. Trefanning, I think that's called, right? When they, right, like drill a hole in your head to let off pressure or something. I mean, it's not like a real thing. It's not in modern medicine. Anyway, how do I get on talking about trefanning from z-scores? I'm insane. So yeah, all a z-score does is tell us how many standard deviations from the mean a given value is, and then it tells us the amount to the left, and it's always to the left. That's the part that people sometimes get tripped up with, right? A positive z-score indicates a data value lies above the mean. Negative indicates it lies below the mean. Yeah, of course it does, right? Because once we subtract the mean here, if the mean is bigger than this number, then we get a negative, right? If this number is bigger than that number, we get a positive. It's not hard to notice, right? Okay, so let's do a few questions on these ones, and let's just jump right into the questions. Your book does have pretty good examples there, Betty Ann. I'm not going to walk down through any of the examples because I do think the book actually does a fairly good job of laying these ones out, like these examples up here, right? Yeah, if you're unsure on how to do these and you want more help, I mean, you can always ask me, and I'll always do some more of them. But the 4 ones in your book there are actually pretty good. Right? So then let's do this here. Determine the z-score for each value of x. Okay? So we're just going to do a few of these questions. Now these are ones that you were asked to do in the notes, but like I said before, right? I'll do all the different questions from your notes, especially now over social distancing because the notes are no longer required for marks. But I strongly recommend you do them because they're excellent ways of practicing all this stuff. The marks from the notes are taken up by the review sheet instead. Right? So we're just given, for these questions, we're just given a bunch of values and we've got to figure out a z-score, right? So these first few questions are just, I mean, practice really. 15.5, let's imagine that I can write correctly, and x equals 174. Okay? So now I've got to do is I've just got to use this formula. My z-score is just going to be my mean, which is 174, subtract my average, or my value, which is 174, subtract my mean, sorry, I think I misspoke there, then divide by 15.5. So break out my mathematical Game Boy over here. 174 minus 112 divided by 15.5. 4. You're not usually going to see a z-score that big, right? That's a bit of an odd one to start with, one that has a z-score of 4, right? And z-scores of whole numbers, well, whole number z-scores are easy, and you'll see why once we take a bit of a look at the table. Let's go through and do out a few more of these. B has the mean is 53.46. The standard deviation is 8.24. And the value is 47.28. So let's find the z-score for that value. The z-score is just, again, right, this is fairly straightforward stuff, isn't it? We've just got to fill in our x here for the first one, 47.28. Fill in the average, or the mean here for the next one, 53.46. And I know calling it the average is technically incorrect, but Excel calls it the average. So anyway. And then fill in the standard deviation down below, 8.24. Then the z-score is going to be what? Well, let's find out. 47.28 minus 53.46. And you see, of course, that makes this step negative, obviously, right? And then we divide that by 8.24. We're going to get a z-score of negative, that's a better one, negative 0.75. Okay? I'm not going to go through all of these ones here in question one, because I think question one is quite a bit easier than what we're going to see later on about z-scores. Come on now, camera, stop that. I don't know why it just randomly gets dark like that. Okay, determine. Okay, sure. Let's play the game. Let's play the game like the way that the book is telling us to do it. Okay, so let's do a few questions from part two. So two gives us a z-score of 1.24, and then B gives us a z-score. I'm going to do both these at once because we've got to flip to a different table to see it. Negative 2.35. So Betty Ann, you can find these tables lots of different places, right? But what, let's see, I'm just going to flip over to the one that's in your study guide. Right, this is, oh, no, that's not the right study guide. This is a different one. This is the study guide. Here we go. Just going to scroll down here. Keep on scrolling. Here we go. So this is the z-score table that you've been provided in your study guide. Now you can find these ones online. Any z-score table that you find should be the same, right? Because it should always show you these same values. And like it says here, or like it shows up in this little diagram here, what we're seeing when we look at the z-score is the percent of the chart, or the percent of the area under the normal distribution that is to the left, right? So just like it shows here, this green shaded part, that's what we're finding. And I know, right, this is a big chunk of numbers here that looks a bit like gobbledygook, and it is poorly formatted, right? They really should have had like the background changing so you could more easily tell the rows and the columns when you got out in the middle of it, but whatever. Right? Not everybody does like formats academic resources for a living, right? I mean, the people that made the textbook do, though, right? So they really should have been expected to do that. Anyway, so if you have a z-score of 1.24 like this, all we got to do is take our table over here, right, and go to the 1.2, which is on this side. So on the left here, right, you see on the top we've got numbers like 0.03, 0.04. What did we do is we combine the number on the top and the number on the side. We add those together, and that gives us the number that we're looking for, right? So if we got 1.24, first up we got to start with our 1.2. That's what we're going to find on the left over here. So we need a positive 1.2. So we're looking in this column, this one across here, right? And then in this column, we need to go find 0.4 because we need to have a 4 afterwards. So the 0.4 is here. So the row rather, not the column. This is the row we're looking in, and this is the column we're looking in. So the number we're looking for is this one right here. So that's going to be, let me put that in a different color here. So that's going to be 0.8925, just like that. Right? So what that tells us is if our z-score is 1.24 when we find it, what that means is 89.25% of the normal distribution lies to the left. Right? So what we could say is a z-score of 1.24, this actually translates directly into percentiles, which is a topic that you had in a previous unit, I believe. So this means it's in the 89th percentile, basically, right? It's whatever the value was, it's greater than 89.25% of all the other values. Right, so then if we look at, say, this other one, negative 2.35, we're going to do a very similar thing over here in this z-score table, right? So we just got to go into the negatives. So we got to make sure to be in the negative column, right? Don't mind this one being red and this one being red. It's just because that's the example they were giving up here. This red part and this red part don't mean anything. So negative 2.35. So we're going to find negative 2.3 on the left, which is going to be right here, right? And now in this row, we're going to go across to 5. So it's going to be right here. So that one is 0.0094. So 0.94 of a percent, less than 1% of the data is going to be smaller, or is going to be to the left of this one, right? So then, of course, if we want to find out how much is to the right of it, obviously it's all the rest of it, right? Because everything under the normal distribution adds to 1, right? The total area under the normal distribution is 1, or 100%, obviously, right? So if we wanted to find out how much is to the right, or how much is greater than this value, we would do 1 subtract this number. Same thing here, right? If we wanted to, this is how much is below the number that has a z-score of 1.24. If we want to find out how much is above it, we're going to need to add, or subtract rather, subtract this number from 1. And that is relevant because that's what we're going to be doing just now, right? So, for example, question 3 here. Determine the percent of data between each pair of z-scores. And this is what I wanted to get onto here was question 3, because this is starting now to summarize sort of the overall point of doing this unit, right? So that we can use z-scores to determine things like this. All right, so for 3A, we have a z-score of negative 2.88 and z equals negative 1.47. We want to find the area between those two, right? So, yeah, let's do these one at a time. Skip on back over here. So now we just got to flip back to our table, and we've got to look those ones up. So negative 2.88, we can find that one. Remember, we go to negative 2.8 over here. Whoa, that's not what I wanted to do. Come on, give me the different cursor. Holy moly, why am I not able to select text all of a sudden? There we go. That was weird. 2.88. Oh, these go from the other side, don't they? That's bizarre. Anyway, whatever. Oh, because it's going down. Oh, I get it. Oh, okay, okay. So 2.8, negative 2.88 is going to be 0.0020, right? And then what we have for the other one, negative 1.47. Negative 1.4 is right here. So the negative 1.47 is this one here. So that's going to be 0.0708, like so. Right? So what does this tell us now? Well, if I was to draw out, just for the sake of drawing out a diagram, if I was to draw out a normal distribution like so, what this is telling me is the first number is really down here, right? So this is z equals negative 2.88, right? And the area beyond this one, so the area here that I'm going to shade in green, that area there, that is going to be 0.0020, right? Or we can call that 0.2%. Right? I know it's getting a bit small here now, but let me zoom in a touch. There we go. There we go. Yeah. Okay. And now the other one that I'll do here in red is going to be negative 1.47. So I could say that's maybe over, I don't know, let's put it over here somewhere. The actual place that I put it on my diagram is not terribly important. This is going to be z equals negative 1.47 over here, so which is 0.0708 or 7.08%, right? And now the area red is going to be this one. But now watch, is it just this area? No, it's not. It's also this area over here. Right? This is the reason I wanted to draw out the diagram, is you see now that the green area is just this bit, but the red area is all of this and this bit. All right, so if we want to find out what's in between, what have we got to do? Well, we've got to subtract, of course. We got to take the bigger one, the red bit, and then subtract the green bit. So if we want to find the, how how did it phrase the question? Let me see here. Between, okay, so the area between is going to be 0.0708 subtract 0.0020, and that's going to equal then 0.0688. Yes. Or 6.88%. Right? Oh, I was scrolled off a little bit. There we go. Right? So that now is going to be the amount of the curve that's in between these two. Okay? I'm running out of space here a little, but I'll do the, let's see. Now, a lot of these, your guide doesn't actually end up asking you to do. The guide doesn't end up asking you to do number 4, I don't believe. Let's look at one more for number 3, just to drive this one home, the way that we do this. This is still page 279? No, it's not. This is page, yeah, I should have wrote down the page number 292. Page 292. This is going to be 3B. And Betty Ann, if you're there in chat and you've got any other ones that you want me to go over, you can let me know. Otherwise, 3B here will be the last one I'll do on this topic for today. And then if you've got any others, you can let me know and I can do them on a future stream. But if you drop in now, if you want me to do some other ones, I can do those now. But I think this is a reasonably thorough look at what z-scores are and how we use them. Okay, so now we just need to go back to the table over here. We're going to need to look up what these ones are. So now z equals negative 0.85. So I'm going to have to find negative 0.8 over here and then get to 0.85, which is going to be this one right here. Right? Yes, so we're still in the 0.8. This is 0.85. So that's going to be 0. That's right, yeah, 1977. Or 19.77%, right? I'm going to do these ones in different colors right from the start, so we see that those are indeed different. And Z is 1.64, so now this is a positive one, so I'm going to go down here, 1.6 right there, and then go over 1.64. Now be careful that they change them on the top. You'll notice this is 0.4 here. Over here it starts from 0.9. That is a little silly, but it's just because it's going down instead of up, I guess. Whatever. Just be careful when you're reading them off the scale, off the table, to make sure to get the right final digit. Right? So 0.4 is going to be here, 1.64. So that's going to be 0.9495. Boy, yes. I shouldn't be looking at the OBS window to see those, because it's scaled down and my eyes are not the greatest. All right. It's not quite a normal distribution. I kind of messed up the left side of it there. Who cares? Doesn't matter a lick. This is just to show you roughly what's happening, right? So the blue one is negative 0.85, so that's almost 1 standard deviation down. So I'm going to say that's going to be about here-ish, right? So this is Z equals negative 0.85, and this is 0.1977. And that 0.1977 is the area below the curve. Right, so if I was to take that and join it up, so then the area, not below the curve, sorry. Well, it is below the curve, yes, but it's below the curve to the left of that line. So the blue area is, this area over here, like so. Then the green one is so it's 1.64. That's about a bit more than 1.5 up. So I'm going to say that's roughly around, I don't know, I'll call it roughly around here-ish. Doesn't really matter. This is Z equals 1.64, and that's going to be 0.9495, and that's how much is going to be below it. And just for illustration's sake, right? And he used a bunch of my precious green ink. No, I did. I did get more pens, by the way. I got some very nice colored, some RGB gel pens. Oh, it's good. I like gel pens too because like when I draw a line, I want the line to actually be drawn. I don't want to have to run over it again and again and again to get the mark dark enough. It gets a bit annoying when you're streaming or something and you've got to or handwriting for a living. Kind of that's what I do when I'm correcting, and then have the right lines over and over and over again to get it to show up. Now, is this all the green? No, it's not. Right? I got to keep going. I got to color all this in green too. Right? Because the green doesn't stop here at this blue section. It doesn't know to. Right? All the Z-score tells us is all the area to the left, every last bit of it, which counts all that was under the blue one as well as what's under the green one. So let me go through and darken this one in a bit in the blue so we can more clearly see that it's two of the colors. Right? So of course now, what have I got to do to figure out the actual area in between? Well, I'm going to have to subtract, right? So the area between is just going to be 0.9495 subtract 0.1977. And I'm going to do that one on a calculator just to show. So I don't want to run the risk of having it wrong because I just did it in my head. Oh, well, it would help if I actually did what I'm supposed to do, right? That would... There we go. 0.7518 or 75.18%. Right? So that is now how much of the data would fall between these two Z-scores. Right? And that's really all that Z-scores are. It's just an evolution of that first topic that we looked at, right? So instead of just picking whole numbers of standard deviations away from the mean, we can pick any number of standard deviations away from the mean that we want. And we find those standard deviations, like I showed earlier, by using the Z-score formula, which might look arcane at the first, but is actually very, very simple, this one here. Because all it's telling us is this part on top finds the distance from the mean, and this divides it by the standard deviation just to find out how many standard deviations it was. And that's then what we call a Z-score. And then we look that up in ye old table. Actually, I mean, my main degree, my master's degree, was in English language and literature. So I should know that it was not pronounced ye and never was pronounced ye. It was the. It was just the character y, right, was used as like a th sound. The th sound in English has actually had a very strange history, and it's been represented by a whole bunch of different letters, including the thorn, right, which is like a p, like a lowercase p and a lowercase b combined, right? Anyway, so it was never actually ye old. It was always the old. It was just the character y represented a th. Anyway, ye old table. Yes, we use this Z-score table over here, and that tells us how much is in between. Well, it tells us how much is to the left. We subtract to find out how much is in between. Anyway, the more things change, the more Peter rambles at the slightest provocation. So to go back over here, stream starts soon. No, it's already going. It's already going there, little guys. Yes, you little guys. Oh my. Flurry looks so happy in this picture. I mean, she's happy in most pictures. Except for when Smokey is bothering her or something, then maybe she gets a little bit of a scowl. I've got a really funny one I'm going to show sometime. I shouldn't tease it. I shouldn't tease the picture and then not show it. But there's one like shortly after we got Smokey of Flurry lying in the dog bed, and like Smokey crammed into the dog bed alongside her, and she has got the biggest scowl on her face. Like it's really hilarious. Because she's about 5 years older than Smokey, right? So when he first showed up, she's like, "Who's this annoying puppy, and when's he leaving?" Then he didn't leave, and she was just eventually got used to him. And now she loves him. But at first there was, a little bit of annoyance from the pesky younger brother, I suppose. Okay, so I'm going to go on with counting problems recap. So Calais, this one is going to be for your courses. And I'm just going to quickly go down through a few questions. Today it's going to be mostly mostly just algebra using the counting problems. I went over a lot of the word problems yesterday, right? And I linked you those ones on stream. I didn't notice at first that I sort of needed to go over these ones, but I'm just going to go down through the lot of these, like all of number 5 and 6 here, so we can just get a good look at the way that we um, handle factorials in algebra, basically. And I do have this one corrected for you now, and I'm nearly done your test, but then I had to, my schedule was calling, and I was doing the stream here. So probably, I don't know, give me half an hour or so after stream is over, and I'll have your exam corrected and sent to you as well. So 5a, have n factorial over n minus 1 factorial equals 4. Right? Now, we know that factorial, it always goes down, right? The numbers always go down. It has to, right? Because if the numbers went up in a factorial, anything factorial will be infinite because you would never reach 0, right? And I know that can be a bit tricky because when we see n minus 1, we think, oh, minus 1, well, the next one is going to be minus 0, right? And then we're going to be done because we're going to have gotten back to n. But that's not really the way it works, right? Because n minus 1, imagine n was 7, right? Then n minus 1 is 6. But 6 factorial isn't 6 times 7. 6 factorial is 6 times 5 times 4 times 3 times 2 times 1, right? So even though it's n minus 1 factorial, it's still going to be n minus 1 times n minus 2 times n minus 3 times n minus 4 all the way through to 3 times 2 times 1. Right? There's actually a better example of that here now in a second. I think in question 6, or maybe 5b, we'll see a bit more on that. But anyway, my point is n factorial is the same as n times n minus 1 factorial. Right? And this is the way that we normally write it out. We don't write this out as n times n minus 1 times n minus 2 times n minus 3 times n minus 4 times 3 times 2 times 1. We don't always necessarily do that, although I could. Right? But I'm just going to show you sort of the way that's more similar to what you were doing in your working, just so you can, and the way that we would write it out normally in algebra working as well. Right? Because n factorial, say 6 factorial is the same as 6 times 5 factorial. Right? But there's only one factorial here. This is another thing, right? The factorial doesn't, this is not n factorial times n minus 1 factorial. It's just n, normal old n, times n minus 1 factorial. So then this one, along with the factorial function, that cancels along with this one, and we're just left here with n equals 4. It's a bit of an easy example to start off with, right? But that is the one there is on your activity, right? So I'm just going to go down through all of these ones. Next up, we have, what is that, n plus 2? Yes. n plus 2 C2 equals 28. Now, this is a good one. This is a good one. These are ones like, well, you do have another test on this topic. I know you just did one today, right? But in the courses you are doing, there is an overall test at the end. So, there is still one more last gasp of NCR and NPR on your tests. So it is worth sort of going over these guys, right? But so we know that NCR, that the normal form, say, of NCR is n factorial over r factorial n minus r factorial, right? And I'll write an NPR over here too. In my aside bubble over here. Okay, so we know that what we're going to have on top is going to be n factorial. So what we're going to have on top is going to be the n plus 2 factorial. And it is important to have the bracket like that, of course, because it's n plus 2 all factorial, not n plus just 2 factorial. That'd be totally different, right? And then down below, we're going to have 2 factorial, which is right here, times then n plus 2 minus 2 factorial equals 28. So how much can we simplify this one now? Well, we see here we can simplify that bit. Excuse me, a sip of water. So we've got n plus 2 minus 2 there. So the plus 2 and the minus 2 are, of course, going to cancel, right? And we're going to be left with n plus 2 factorial over 2 factorial, which I can just call 2. I can not write that in because 2 factorial is just 2 times 1. So I'm just going to not bother to write the exclamation mark there. And this is just going to be n factorial equals 28. Now I can keep going and I can simplify this a bit more, right? Because I know that n plus 2 factorial is the same as n plus 2 times n plus 1 times n factorial, right? And down here, we've got 2 times n factorial. And that's still equaling 28 over here like so. But now, right, this part and this part are not factorials anymore because I've just sort of taken a factorial and started splitting it apart a bit, right? Because remember, say if n is 8, right, then this is 10, and this is 9, and this is 8 factorial, which makes sense, right? Because 10 factorial, or 8 plus 2 factorial, right, would be the same as 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. So at any point along the line of that factorial, I can just sort of stop writing them down and just call it the remaining digit factorial, which is not just a cop out. It's a way of representing what we're going to be able to cancel out of this, right? So I know that I can cancel this with this. Now this 2 stays there though. I know you might be tempted when you think about this to remember that, hey, there is going to be a 2 in this eventually. Yes, there is. There is going to be a 2 in this part eventually, right? Because it does go down to times 3 times 2 times 1 at the end. But there's also a 2 in this one, right? Because this is n factorial as well. So this has a 2 in it as well. So we can't cancel this 2 with the 2 out of this part because it's already spoken for. It's already canceled with the 2 out of this part. So this 2 has to stay here. But what do we do with it? How do we get rid of that 2? Well, it's just a divide by 2 in an algebra problem. How do we get rid of divide by 2? Well, we multiply by 2. We multiply both sides by 2, right? So what we can do is we can multiply this side by 2 and then this side by 2. Right? And I'm just doing that now to get rid of this one. So we end up over here with n plus 2 times n plus 1. And it doesn't equal 28 anymore. Now it's going to equal 56 because it was double that. Right? And now we can go ahead and just solve this one because now what we've got is just a quadratic. This is just a normal ass quadratic that you've seen, well, yeah, I mean, you've seen loads of times before. Right, so it's going to be n squared plus 2n plus n plus 2 equals 56, or n squared plus 3n, and I'm going to subtract the 56, minus 54 equals 0. So now we have to factor a quadratic, right? We need two numbers that are going to multiply to give us negative 54 and add to give us a positive 3. Well, how are we going to get those, right? So our negative 54, well, what can that be? That's going to be 2 times 27. Those aren't going to make 3. Was that 3 times 18? Yes, that's right. 3 times 18, that's not going to work either. Or 4 is not going to work. 54 divided by 5 is not going to work. 54 divided by 6. Well, that one works, right? 54 divided by 6 is going to be 9. So 6 times 9. Hey, that one works, right? Because we can't add those guys together to get a positive 3. We know that it can be positive 6 and negative 9, right? So we know now that we're going to break this one down into n minus 9 and then n plus 6 equals 0. And remember, the final step now for our factorizing is saying what values of n are going to make this case true. Well, either this bracket needs to be 0 or this one needs to be 0. So either n needs to equal positive 9 or n needs to equal negative 6. And we know now, if we look back up here at our beginning, we had some NPVs in this one, didn't we? And like I mentioned, it is useful to write out your NPVs all the time, even if you're not asked for them. But here, remember, our NPVs have to be such that, excuse me, my lord, we can't divide by 0, but also we can't take the factorial of a negative, right? So we know here, because there's an n factorial down here, that, well, I know we start off with this one up here, like I've always said, right? We always start with our original, but this is a little bit different, right? Because this one's just an add and subtract. So that's kind of like it's not there right from the start. So here we know that n has to be greater than or equal to 0, right? So since n has to be greater than or equal to 0, this guy doesn't count because that's a non-permissible value. So n equals 9 is going to be our solution. There we go. Right, so that one had a few more steps than the other one did. But once we got down to, really once we got past this step, all the math there on out was stuff from a previous unit. It's not to say you don't need to know it. It's not to say it's any less relevant, right? You're still getting marked on it. But, you know, the math from this unit sort of ends once we do this canceling. All right, so let's do, see if I can cram C in over here. So that's n minus 1 p2 equals 42. It's going to be very similar to the one we just saw, of course, right? But the p's are up here. So we know that this is going to be n minus 1 factorial over n minus 1 minus 2 factorial equals 42, which is n minus 1 times n minus 2 times n minus 3 factorial over n minus 3 factorial. Right? Now it's important to know for these ones, like I was just saying, that n minus 3 factorial turns into n minus 3 times n minus 4 times n minus 5 times n minus 6. I know it's tempting to think that n minus 3 factorial is going to go the other direction. It's going to go n minus 2, n minus 1, and n minus 0, or just n. But it's not, right? Because these are negatives. Right? So it's all, our number is always decreasing, right? Because like you know, like we say a whole bunch of times, you can't take the factorial of a negative number. So it's not that we're always going down towards 0. So we're always decreasing, right? So n minus 3 factorial, you know, if n was 2, we just wouldn't be able to do it, right? So we know this is a positive number already. It has to be, right? Because that's going to be our, like I was just mentioning, right? Our NPVs for this one has to be n is greater than or equal to 3. Anyway, so once we get to this stage now, the n minus 3 is going to cancel with this n minus 3, and we're just going to have n minus 1 times n minus 2 equals 42. And at this point now, again, we've got a quadratic just like this action over here, right? So this is going to be n squared minus 3n plus 2 equals 42, or n squared minus 3n minus 40 equals 0, right? So we're going to need to go over here and get our negative 40. Well, 2 times 20 is not going to work because we got to get to negative 3, right? 3 doesn't work. 4 times 10, that's not going to work. 5 times 8. Hey, that's going to work. That does work. Yes. So a negative 8 and a positive 5. So n minus 8, n plus 5 equals 0. Rather than that our n is positive 8 or n is minus 5. This one's an NPV. This one here is the solution. All right, so I am gonna keep going on these ones. I think I'll get these next 3 ones done as well, and then if I've got time, which I probably should, I'll do a brief look at. I keep saying I'm going to do volume of regular shapes, and then I don't. It's not a super difficult topic. I just want to do a little bit of an intro to it at some point. Math, yes, it's still 3101A, and it's still Unit 2. This is going to be 5D over here. Now, the way these ones are written, right, this is n plus 1, and then a 1 like so, equals 14. So this is something I'll put over here. X over y, like that, means xcy, not p. That one's always xcy, right? So what we have here, when we have this, that's actually n plus 1 c1 equals 14, which we know becomes n plus 1 factorial over 1 factorial times n plus 1 minus 1 factorial. Now, this one actually doesn't matter because it's 1. I know that when we're choosing 1 or 0, right, the NPR and NCR are actually the same. So that Calais, that came up on, I believe, one of your questions. You'll see when I send you the notes for it shortly after we're done here. Um, I, that you can still get the right answer but have the wrong working, because sometimes you need to use C, but if you use P, the answer might still work out to be the same, because, like I said, something C1 and something P1 is going to be the same. But anyway, it's a really minor point, but it is worth mentioning. So what we have over here now is going to be n plus 1 times n factorial divided by n factorial, right? And this 1, well, multiplying or dividing by 1 doesn't do anything, so I'm just going to not write it down, because you could write down as many 1s as you wanted, right? Equals 14. So this n and this n factorial are going to cancel. N plus 1 equals 14. Well, this is not hard now, is it? N equals 13. Okay, let's go on now to 6a over here. So 6a is the same sort of deal. This one says simplify instead of solve, but it's basically the same thing. Simplifying is generally just less work than solving anyway. N plus 2 factorial over n plus 1 factorial. Well, how can we expand these two, right? N plus 2 factorial. Remember, that becomes n plus 2 times n plus 1 times n, so on, down to 3 times 2 times 1. I'm just going to write it out like this again. Like, I know earlier I said I wasn't going to do this, but just to show you really what's going on here, right? And this n plus 1 is going to be n plus 1 times n minus 1, and so on, all the way down to 3 times 2 and times 1. So, of course, now you'll see that all of this bit is the same as all of this bit. What we're left with is just n plus 2. Right? And that makes a whole lot of sense when you think about it. Like, just if you're not completely sure on how to do these questions, I strongly recommend just pick some values for n and see what happens. Just try it out yourself. You can even use your calculator to find out. But imagine n was 7, right? Let's just randomly set n to be 7. N plus 2 is 9. N plus 1 is 8. What's 9 factorial divided by 8 factorial? You could even do it in your calculator if you weren't sure, right? But 9 factorial over 8 factorial is just 9, right? So if n is 7, the answer here is 9. If n is 2, let's say I pick n to be 2, this is then 4 factorial over 3 factorial. 4 factorial over 3 factorial works out to be 4, right? So if n is 2, the answer is 4. Sounds like each time the answer is always 2 more than n, right? So it's just a way to sort of build some resilience, I guess, in math questions like these. If you're approached with something, say in a test or another sort of pressure situation where you need to get the question right and you need to get it right then, just try some things like putting in numbers for n and seeing what it works out to. It's a really good way of getting a solid hint to what if you're working is right or wrong, basically. So one is n minus 4 factorial over n minus 2 factorial, like that. Now here is a situation where students oftentimes are really tempted, and this is a common mistake that you see, to say n minus 4 factorial is n minus 4 times n minus 3 times n minus 2 times n minus 1 times n. But it's not. It's not at all, right? Remember that n minus 4 factorial is n minus 4 times n minus 5 times n minus 6, and then so on, all the way down to 3, 2, and 1. The same token, n minus 2 factorial is n minus 2 times n minus 3 times n minus 4 times n minus 5, and so on, 3, 2, and 1. Right? The number of ones that I write out when I do this is just arbitrary. I'm just sort of randomly picking. Right? But when you write it out like this, I think it starts to become a little bit clearer that what you're actually got now is this n minus 4 on down. This cancels with this n minus 4 on down. And we're left with 1 over n minus 2 times n minus 3. And the book now, or the answer key to this, does tell me to have you go on and sort of multiply these ones out. I'm not 100% convinced that you should, right? Because usually when we approach quadratics, a factored quadratic like this is considered to be simpler than multiplying it out. But if you did multiply it out, you would FOIL these guys, and you would end up with n squared minus 5n plus 6 down below. Right? Now, I would give you full marks for this step. Right? I would say that you're done there. This is correct too, but I wouldn't dock marks for leaving that last part off. Okay? So Calais, I think that was all that I wanted to mention so far for your topics. Like I said, I'm partway through correcting your test, and I will get that finished now shortly once I'm done here today. Doing really well so far, so nothing to worry about there. Boy, oh, mouth is dry today. Oh, I moved my camera a bit. Move my camera a bit. Real world's bleeding in. No, get it out of here. Get that real world out. Okay, good. Good. Back to the glorious internet. Get that meat space nonsense out of here. Although says the streamer who's using a face cam, right? I could just, I guess, not have a face cam. It wouldn't really detract all that much from my stream, I suppose. But I don't know. I think it adds a certain charm, right? That's what I tell myself. Yes, so now I'm going to go ahead and do a little bit on volume of regular shapes. So, Carly, this is going to be for your material. Now, you're not necessarily going to be getting into this immediately. You do have 5 pages of your previous course to do. Please do them. Like I see those notes that you sent me, and those, but you know, if you check those notes, you'll see that those are the same ones that you sent before. So just please go over it and do those few missing pages. It's not very much, they're not very hard. They're actually even easier than the pages that you have done. So I'm not concerned that you can't do them. It's just, you know, it's just a few pages of questions that need to be done before you go on and do your test. That's all, right? I believe it's pages 157 to 161 in your text. I mean, and you can see them, right? The page numbers are in the corner. People, we know how page numbers work, right? That's not, you know. But that's all it is. Like they're not difficult. It's not a big deal. Just, you know, I do want to have the full notes done before you go on and do your test in that. But once you write the test in that unit, then you will be on to a unit where you're doing area and volume of regular shapes. Now I did an introduction to area a few weeks back on stream, and I did the pre-test to the area section, right? Because your next unit is kind of 2 small units mashed together. And this is the second of those 2 small units, and this one is on volume. This is going to be Math 2017, and this is volume of regular shapes. I should say regular solids. So volume of regular solids, all it is you just take the area of a face and times by the height. Or area of base, I should say. Area of the base times the height, right? Because of course the height is at 90 degrees to the base, basically. Right? But all you're doing, the volume of any regular shape is just the area of the base times the height. And by a regular shape, I mean a shape that has the same dimensions all the way up. It doesn't taper, right? It's not like a cone or a pyramid. Those ones, we do have formulas for those, and you will get into those eventually. But for this unit now, you're starting off with just the regular ones, which are just going to be these shapes you see over to the side here. Rectangular prisms, triangular prisms, and cylinders, right? So there's 3 basic formulas that you're going to need to know, right? So the volume of a rectangular prism, otherwise known as, you know, a box, is just going to be length times width times height, right? And this is the area. Length times width is the area of the base, because of course this one is rectangular, right? So the area of a rectangle is just length times width, and then we're going to multiply it by the height of the shape, right? So it's not any different than what I said. It's still volume is the area of the base times the height. Just in this case, it just happens to be that it works out for all 3 of the dimensions just multiplied together like that, right? Fairly straightforward stuff. So for 1A, right, we can see in 1A that our length, right, let me just get my cursor over there. Okay. We're seeing it? Yeah, we're seeing my cursor here now. Okay, so the length, I'm going to call this one here. So that's going to be, is that 6 meters? Right? The width, I'm going to call that 3 meters. Right? Because the width is going to be, boy, this one here. And the height is going to be that one there. So then the volume is just going to be length times width times height, or the volume is going to be 6 times 3 times 2, which is just 6 times 6, which is 36 cubic meters. Now we put this cube in the corner because now we're talking about volume, right? And volume has 3 dimensions, like we said before, right? Area has 2 because area is flat. Area is like a piece of paper, sort of. Like the space on a paper is area because it's 2-dimensional. We're used to, even though we live in a 3-dimensional, 4-dimensional world, we're used to thinking of 3 spatial dimensions. We're used to thinking of things in 2 dimensions a lot of the time because of screens and books, right? Because of paper, stuff printed on paper, stuff shown on screens have 2 dimensions. But like I mentioned before in a different course, you've never seen a 2-dimensional object. There aren't 2-dimensional objects in reality because we live in a reality with 3 spatial dimensions. So everything you see is 3-dimensional. Even a paper, even a sheet of paper does have a height, right? It's small. It's quite small, to the tune of what, like, I don't know, a tenth of a millimeter maybe or so. I don't know. I don't know what the thickness of a piece of paper is off the top of my head. But it does indeed have a thickness. It's not, it's not just 2-dimensional. And like I'm saying, volume easily obviously maps to the real world because it's just how much space a shape takes up in 3 dimensions is all we're saying. Right? So B here, we're going to have, well, that's a cube. That's a cube, right? So the length is 4 centimeters. The width is 4 centimeters, and the height is 4 centimeters. So the volume is going to be 4 times 4 times 4, which is going to be 64 centimeters cubed. Right? And I knew that one off the top of my head because that's a cubic number. 64 is 4 times 4 times 4, or 4 cubed. Hence why we call it cubed. Because the dimensions, because if a cube was 4 dimensions in each direction, then it's going to end up being 64, whatever the units are, in volume. And the next one, 7.5 times 3 times 3. 7.5 times 9. Well, I know that 7 times 9 is 63, and half of 9 is 4.5, so it should be 67.5. All right, but I will do it on the calculator just to show you, and just to show myself, honestly, not really show you, right? Never trust, not never trust yourself. I mean, that's a bit dark, but you don't have to. You don't have to trust your own mental arithmetic in a situation like this because you've got a calculator. So why risk it? Why risk getting a question wrong when you could just plug it into a calculator and then be guaranteed to be right? I mean, so long as you plugged it in correctly, I suppose. You're never guaranteed to be right. A greater chance of being right. Okay, so now the volume of a triangular prism. So again, it's going to be the area of the face. Boy, oh boy, did that get dark. What is going on with this camera? Okay, so it is still the area of the base times the height, but what is the area of the base? Well, what is the area of a triangle? The area of a triangle is a half of the base times the height, right, of the triangle, and then it's going to be times the height of the shape. But you'll see it sometimes written as, written a little bit differently than this, but basically that's the area of the base, area of the base times the height, right? And I'm going to use lowercase b and lowercase h to represent those ones because we're looking at the height of the triangle there, right? But for a here, let me zoom in a bit. Let me zoom in a bit. I don't need to be showing the full page at once, do I? There we go. Boy, it's almost like computer technology can zoom in on things for us. We don't need to use our eyes that are addled with keratoconus. Anyway, so 2a then. So the base or the lowercase b is going to be 20 because I'm looking at this as a triangle, right? You see this triangle here, right? This triangle is the base of the shape. So that one has 20 across here, and then the height is going to be at 90 degrees to it. That's going to be there, and it's going to be 5. Right? So that's the height of the triangle is 5 centimeters. And capital H, or the height of the shape, right? The height of the full shape here is 10. So we can see that right there. So the V is going to be then a half times 20 times 5 times 10. The volume then is going to be 10 times 10 is 100 times 5 is going to be 500. 500 centimeters cubed with a 3 in the corner, like so. Right? And you can think of this as length times width times height divided by 2, because you can also think of a triangular prism, just like you can think of a triangle as half of a rectangle, you can think of a triangular prism as half of a rectangular prism. But I think the better way to think of it in general is that it's the area of the base, so in this case, the area of this triangle, times the height of the shape. Right? So let's go on a bit here for B. Right? We know our volume is going to be a half BHH. Right? Or it's kind of that. It's kind of half of the length times the width times the height, but I'm not really going to write it out in those terms. I'm going to keep using these terms because you're used to seeing this part here, meaning the area of a triangle, because we looked at that before, and it's the area of the triangular face times the height of the shape. So I prefer writing it like this because it scaffolds better, which is a teachery way of saying that it builds on the previous stuff that you've learned. So the volume here is going to equal a half times 4 times 3 times 6, right? Because we see 4 is the base of the triangle, 3 is the height, or vice versa. It doesn't matter which is which there. It just matters that they are offset by 90 degrees. And in this case, indeed, they are offset by 90 degrees. We can see a 90 degree right there. And then 6 is the height of the shape. So that one then is going to be half of 4 is, of course, 2. 2 times 3 is 6. 6 times 6 is 36. 36 millimeters cubed. And again, right, cubed, 3 in the corner. That's important. Right, your units are really important. In this course, I'm not going to subtract much for your units. I might not even subtract anything for the units in some of these cases. But you are going to be docked for units eventually, so you do need to get the practice down of including your units. So again, the volume is a half BH, a half of the, right? So this is the area of the triangle face, and then times the height of the whole shape. The volume then in this case is going to be a half times 2 times 1 times 1.6. Well, that's easy. A half of 2 is 1. 1 times 1 is 1. 1 times 1.6 is 1.6. This one is 1.6 meters cubed. There's our final answer. Easy peasy. Right? Now the next one we're going to look at here is the cylinder. So the volume of a cylinder, again, it's going to be the area of the base times the height. But what is the area of the base when it's a cylinder? All right, what's the area of I guess, we're showing down here, the area of this part? Well, that's the area of a circle, right? And the area of a circle is pi times radius squared, right? We're told that. And then, like we set up here, it's the area of the base times the height. So we're going to then multiply that by capital H, or the height of the full shape. So 3a. Yeah, I'll keep modeling good behavior. I guess I didn't do it over here, but I'll declare my variables over here. We can see from this shape here that the radius, or r, is going to be 5. And we can see that the capital H, or the height, is going to be 9. And for a cylinder, we only need those 2 measurements and we're good to go. Right? So our V is equal to pi r squared h. So the volume is equal to pi times 5 squared times 9. Volume is equal to pi times 25 times 9. Volume is equal to 225 pi. right? And like I said, in later courses, we can sometimes leave our math like this, just call that 225 pi and be done with it. But for this course, like it says over on the side here, we're going to use 3.14 for pi. So we're going to go ahead and multiply 225 by 3.14 and get a 706.5. 706.5 meters cubed. Cubidoob. Because there's 3 dimensions. Now, 3b. Let's keep on going. Let's get these next 2 done. And then, yeah, that'll be a good look at sort of an introduction to this topic, I think. So for this one now, this one has a bit of a wrinkle, doesn't it? Right? Because we're not given the radius here, we're given the diameter. You notice that we're given the diameter here is equal to 8. So if we're told that diameter equals 8, remember that radius is equal to a half the diameter. So here the radius is equal to a half times 8, or the radius is equal to 4. Right? It's always important to watch out for those, because sometimes you will indeed be given the diameter, and you can't just go ahead and use the diameter. You have to convert it to a radius. Right? So this one is going to be volume is still going to be equal to pi r squared h. So the volume is going to be equal to pi times 4 squared times 10. Volume is going to equal 160 pi's. So it's going to be exactly 480. No, it's not. 502.4. Yeah, see, I hadn't, it's been a solid like 3 streams since I referenced that same Simpsons gag that I keep referencing. Oh, pi is exactly 3. Sorry it had to come to that. That is one of my favorite, just like throwaway Simpsons jokes, although there's a lot of them. The golden age of Simpsons, like seasons, I don't know, 1 to 12 maybe? Maybe I'll go so far as to include 11 and 12. And even I would even include season 1. I mean, season 1's pretty rough, right? Season 1 of The Simpsons, there's a lot of stuff that doesn't really maintain, like the relations between the characters are not well established at that point. So I'm okay with writing off season 1, I think. But like 2 through 10 is definitely like that's. I think that was pretty much universally considered to be the best part. But I think we can expand it to 11 and 12. It's got some good seasons. The grimy episode. That's one of my favorites. That's easily. You've been to space? What, you haven't? Anyway, I don't want to just keep repeating Simpsons references over and over here. Or do I? Yes, I do actually. That was a lie. That was a bold-faced lie. I do want to. I'm just not going to. 1356.48, and that is what's our units? Millimeters cubed. Right, for the last one, I forgot to put in the units. That was centimeters cubed. And there we have it. Right? So Carly, it's really all you're going to need to know for that second part of the unit. Oh, I'm still zooming in. The second part of that unit that you were getting onto. Right? So there you go. There's your Chapter 12 pre-test. Like I said before, that is a page you're not responsible for doing, which is why it's a really good example for me to go down through it. I'm going to skip question 4 there. It's just one more example of each, and we've already done 3 of each, right? So a fourth, whatever. We're good, I think. And that will be all for today. Right, so I think it was a good look down through those few topics. Like I mentioned, well, Kelly and others, if you're still watching, you will get those notes very shortly. And Kelly, you'll get the grade in both your test that you did today and the assignment you submitted yesterday. Okay. Well, thanks very much for being here with me today. I hope that was engaging, entertaining, compelling, riveting, and sleep-inducing. It's at least one of those. Yep, thanks for being here. Stay safe out there. I hope to see you all again tomorrow. It was arousing. Well, okay. Sure. I mean, I'll take that. You know, but yeah, I mean, it's over the internet, right? So I don't I don't 100% need to know, but I mean, I can appreciate a compliment, I suppose. Right. Thanks very much for being here. Yeah, and I hope to see you again tomorrow.